So far in this school, you have learned many things about high energy physics theory, and then experiment. You have also learned, I guess, or you have seen lectures or attended lectures on ALICE detectors, and also somebody wrote something on chat. Yeah. Okay. So, and also you have learn the data analysis process, error analysis, statistical aspect, statistical analysis of physics and high energy physics and experimental physics. Okay, so now I will be mainly showing some pictures and will tell you how to make detectors. Mostly I will try to cover the fabrication of detectors, what we have done in our lab or in other collaborating institutes by our collaborator, Indian collaborator. Okay. So and if you have any question, you can stop me anytime. I will go very slowly and I will show mainly pictures. So if you have any question, you can ask me or you can write to me by email. Okay, so the main topic is definitely fabrication of detectors or making of detectors, but why we need detectors? So basically we will do radiation measurement, and the basic operation principle of different type of radiation detectors that we have to understand. Although I will not go into the detail interaction process and operation principle of all detectors. I will try to cover some of them, and the physical process underlying the principle of operation of these devices, that also we have to know, we have to understand properly before fabrication of any detectors. And finally, in a particular experiment like our ALICE experiment, CBM experiment, STAR experiment, we have to choose the detector or instrument according to our purpose. Okay, so accordingly we will select the detectors. So basically in the ALICE setup, experimental setup, we have seen many detectors, but all the detectors are mostly classified into three categories. One is gas field detector, which is the oldest detector of all detectors in the world, and then comes scintillation detectors, and finally solid state detector. Nowadays these solid state detectors are used in many experiments, although other two detectors, gas detectors, scintillator detectors, are also used in all kind of experiment now we are performing. Okay, so first or I will mainly cover basically two types, gas field detector and scintillation detectors, where I have worked in my lab, in our laboratory, and I will give my experience. So in these two detectors. The first comes the gas field detectors. I will show only one slide. I think I have only one slide how the gas field detector works. What is the basic principle? So it is very simple. There are basically two electrodes. One is called anode, another is called cathode. These two are usually made by metal, and a electric field is generated by applying power supply. So there are many detectors. High voltage is applied in many different ways in many detectors. So this is the just one schematic, which is I mean this is a general gas field detector. So this chamber, so as the name is telling, gas field detectors, so you need a chamber which will be filled with gas, proper gas. So you have to keep in mind that there should not be any leak. Then you are thinking that this chamber is filled with some gases, but if there is leak, then air will be diffused or outside gases will be diffused to the detector. So then it is not the gas or desired gas, where you are thinking that this chamber is filled with some proper gases, so it will not be the case. So this chamber must be leak free. So as much as possible, I will not tell leak free, but you have to minimize this leak issue. Now, so this chamber is filled with gas. Now, if any radiation means any charged particle or gamma ray or X-ray, any kind of radiation, if incident, there will be a ionization. Now, ionization means production of electrons and ions. Okay, so electrons and ions will be produced, and this will immediately recombine, because if there is no electric field, it will be recombined. But as I told, I will apply some electric field in the chamber using the external power supply. So there will be an electric field. Now, once the ionization takes place, electrons will try to go towards the anode, which is positive, and ions will try to move towards the cathode. So this is a very general and basic principle. Now, question is how fast these electrons and ions will move. So all of you know, I think, that electrons are very light particles, so they will move very fast, and ions will move very slowly. Now, once the incident charge particle enters the gas volume, there will be some collisions with this charge particle and the gas molecules, and some electrons and ions will be produced. The number of electrons which are produced by this interaction only, that charge particle enters, it collided with the gas molecules, and some electrons are produced. These electrons are called primary electrons, and this process is called primary ionization. Okay, so once the incident particle ionizes the gas atoms or molecules, this process is called primary ionization. Now, as there is electric field, these electrons will try to go towards the anode, and because of electric field, it will get some kinetic energy, and because of this kinetic energy, it will collide more and more in the unionized molecules, and it will produce more and more electrons. And this ionization is called secondary ionization, and these electrons will be called secondary electrons. And once these processes are continued, then you will find suddenly a cluster of electrons, a bunch of electrons, and this is called an avalanche. So you can say an avalanche is created inside the gas, and once the and this cluster or this avalanche of electrons will try to move slowly towards the anode, and ions will try to move towards the cathode, and because of this movement you will get a signal. And there are many ways how these signals are collected. You can measure the current, this ionization current, and you can tell, yes, there was ionization. You can see signal from the anode wire, or there are many ways how the signals are collected. I will not go into the detail of this, so I just told the basic principle. Okay. Now I will show the ALICE detector. This I think Sanjeev has already shown you. So there are many kind of detectors. Maybe today you know better than me all the names, so I will not go into the detail again. So there are many detectors: TPC, time of flight, FOSS, ITS. So you see, many of you are doing data analysis, and you usually tell, I am using the signal from TPC and TOF, right? So this TPC and TOF, these two are definitely gas field detector. TPC stand for time projection chamber, which is a gas field detector, and another TOF is RPC, which is used in the TOF. Okay. Now, this time projection chamber, you have used, or whoever is doing data analysis using the first two runs, run 1, run 2, this times data. So you know this time this TPC readout plane was basically with multi-wire proportional chamber, and nowadays when we are starting run 3, 4, here we will be the particle rate is increased. All of you know about this, and because of high rate handling, we have replaced the multi-wire chamber by gem detector. So nowadays this gem is one of the important detectors for many experiments, and ALICE is one of them, where we are using gem for handling high rate of particles. So this is another view of ALICE. Many of you, I think, who entered the ALICE cave have seen this. I have not seen because I have not entered in this area, but I know many of you have seen during the dismantle of ALICE detector at the end of run 2. I know. Okay. So now this is another view of ALICE TPC, where you can see the detail of ALICE TPC. You can see this is one of the largest TPC. I think the largest TPC in the world at this moment. So this is 5 meter in length, and the diameter of the detector is again 5 meter, and the volume is 90 meter cube, which is very high. And in the run 1, the neon CO2 gas mixture was used, and here also we are using neon CO2 gas mixture. And I am not going into the detail of the physics why we are using this gas and all, but definitely you can go into the TDR of this TPC and other detectors where there was upgrade, and you can see the details of all these detectors. So basically this yellow part is called the drift plane, drift electrode, where very high voltage is applied, and there is a field gradient using the field cage in the TPC, and at the end cap, where in the first runs there was multi-wire proportional chamber, and they are now replaced by gem detector. So there are two parts. You can see IROC. IROC means inner readout chamber, and OROC means outer readout chamber. So these are quite big chambers, and large gem detectors are used for this part. Basically, in this IROC part, there was only one gem foil, big gem foil used to make the detector, but in the OROC, which was much bigger than the IROC, there was 3 parts: IROC 1, this part, then IROC 2, and IROC 3. 3 parts were there to make one IROC detector plane, OROC detector plane. Okay, so these are quite big detector, and total 18 such IROC and OROC was there in each side. So in the 2 sides, these chambers are placed. Now they are operational, and I think data taking is already started with it. So now I will show another detector setup. This is compressed baryonic matter compressed baryonic matter experimental setup at Fair, Germany. There also we will use different detectors. You can see TRD, TOF, ECAL, MVD, STS. These are silicon detector, but this TRD, TOF, and you can see another is called muon chamber match. These detectors are gas field detector, and particularly in match, where India is participating, India is making the detectors. Here also we will use gem detector in the tracking stations. So there will be 3 detector layers, and first 2 stations. So here and in here we will use gem detectors. And I missed one thing in ALICE TPC. These gems are quadruple gems. Quadruple. I will come onto it. But quadruple gem means one detector is built with 4 gem layers, 4 gem planes. But in CBM experiment, we will use triple gem. Okay. So now I am talking about gem. So what is gem? Gem stands for gas electron multiplier. Okay. So this is basically a thin Kapton foil. Kapton means you can think of some plastic, very high resistive plastic of 50 micron thickness, and on top and bottom of it there are coppers of 5 micron. So this is very thin. Some you can say that's why we are telling gem foil. Foil means you have used aluminum foil, so they are very thin. So total thickness of one gem foil is only 60 micron. So that's why we are telling gem foil. So gem or gem, when we are talking about gem, you will think that this is I am talking about gem foil, and when I am talking about detector, that means we have used several gem foils to make a detector which will give you signal. Okay. So how a gem foil is made, I told. So this is very thin Kapton with copper cladding on both sides, and using photolithographic technique, large number of holes are created in the foil. So you can see here a hole of diameter 70 micron is created by photolithographic technique, and the distance between two consecutive holes, it is called the pitch of the foil, and this is 140 micron. So now you can imagine how small holes are created to make the gem foils. These are done at CERN, but nowadays in India also there is one company in Bangalore, and in Hyderabad another company. They have also started fabrication of at least small size gem foil. So nowadays in India also gem foils are built. So this is called standard gem foil, but in ALICE we have also used non-standard gem foil where the whole diameter is 70 micron, but in some of the foils the pitch is quite large. This is 280 micron, and they are called large pitch gem foils. These are basically non-standard gem foils. So this we have used in ALICE for one special reason, that is called to minimize the ion backflow. Okay. So now how this gem foil is used as a detector? Now you can see there are holes. Okay. So holes of diameter 70 micron. But if you go into the detail microscopic, if you see the microscopic view of gem foil, although there are many geometries nowadays available, but in a standard gem foil, this area, this region, this diameter is 70 micron, as I told. Here it is 50 micron, and here it is again 70 micron. And this shape, whole shape, is called biconical. So nowadays there are gem foils having biconical hole. There are gem foils where there is this conical hole, where it is 70 micron and this is 50 micron and this is like this. So there are many kind of gem foils. So I am not going into the detailed classification of gem foils. But in a standard gem foil, let's say this is 70 micron, this is 50 micron, and this is again 70 micron, and this thickness 60 micron. So this Kapton insulator part is 50 micron. Now if you apply some voltages, some means say 40 kilovolt, 400 volt in this 50 micron gap, how much electric field you can create? Can anyone tell? If you calculate just V by D, is simple calculation. You have applied 400 volt, 50 micron. So what is the electric field? If you do V by D calculation in kilovolt per centimeter unit, Can anyone tell? So all are sleeping, I think. Or nobody can. Am I audible? All are sleeping, I think. Obi, can you hear me?
Audible. Yes, sir, you are audible.
Okay, Obi can hear me, but anyone else? Original Shayok, can you hear me? All are Bose Institute people. Oh, somebody wrote in the chat box, I think. Okay, fine. Okay, so it is 80 kilovolt per centimeter. Good. Now, okay. So if such a high electric field is created in the hole, now if there is any radiation incident here, somewhere here, somehow it produces some electrons, let's say some number of electrons, n number of electrons. Now, if there is also some electric field created, it is actually created by some means, I will show very soon. So some electrons, because of electric field, will try to go here and will try to cross this hole. Now, if the electric field here is something, say 3 kilovolt per centimeter or 5 kilovolt per centimeter, and suddenly it goes in a region with 80 kilovolt per centimeter, so there will be some kind of interaction with gas molecule and some avalanche will be created. So these electrons are called, which are produced here, is called primary electrons, and the electrons which will cross this gem part and which will try to go here, there will be avalanche and electron number will be multiplied. That's why this name is called gas electron multiplier. So gas is here, electrons is multiplied inside the hole. That's why the name gas electron multiplier. Now, this is the trajectory of electrons. So when the primary electrons try to go through the hole, there will be multiple collision and multiple ionization. Secondary electrons will be produced, and because of electric field, mostly electron try to go here, but some electrons will also absorb here. So this is the movement of the electrons inside the hole. Now ions will go here, and the electric fields are arranged in such a way, I mean created in such a way, the ions mostly will be collected on top of the gem foils, but still some ions will go here, which is actually we don't want these ions to go somewhere here, but you cannot stop all the ions, so some ions will definitely go in this region. So now here you can see a better picture or some schematic. Let's say this electrode, I have not talked about this electrode, now I am telling. So this is gem foil, what you have seen here, this is gem foil. Now before this gem foil, where I told the primary ionization took place, this region is called drift region, okay, and this electrode on the top, it is called drift electrode. So in any gem detector, first we need an electrode called the drift electrode, then the main gap, this gap is called drift gap, where the primary ionization takes place, and then these electrons try to cross the gem holes, and the secondary electrons are created inside the gem holes because of high electric field, and then these electrons will go in the next part. Now you can do one thing, you can put one electrode here, like I have put here, this called PCB or readout PCB or readout plane. If you can put here, you can see a signal somewhere here, but the problem is to get a detectable signal, very good signal where you can distinguish between signal and noise. So we need some electrons that you will get a detectable signal. For that, we need more electrons. So to create more electrons, two things you can do. One thing is that you can change the gas, and you can tell I will take a gas where this primary number is much more, and then there will be one avalanche, and then I will get much electrons here. Yes, you are right. You can tell no, I will use the same gas, but I will increase the electric field somewhere here. So the multiplication will be more inside the gas, this gap, and here the electrons will be more. Yes, you are right. That is another option. But you can do another option. You will not change the gas. You will not increase the electric field here much, but you can increase the number of gem plane or gem foil. Why? In that case, when you increase a voltage somewhere here, then you are pushing your detector to a region called the discharge region, because if you apply very high voltage, lot of electrons are produced, then there will be a discharge, then there will be spark, and you will not see any signal during the spark time. So you will again see signal after the spark is over. But since you are building your detector for high energy physics application, so you want that my detector will be discharge free, such that I can register all the particle, I can measure or count all the particles. So that's why what we usually do, we use a standard gas mixture where all the purpose are solved. Then we use little voltage. Let's say instead of 400 volt, I can use 350 volt in one gem foil, but I can use multiple gem foils, such that individual gain of each gem foil will be more. And from this schematic you can see here the number of primary electrons, then number is increased because of ionization, then again increase, then again increase, and you have collected those electrons and you are getting signal using preamplifier. So that's why, and this technique is called, or this is called cascade of gem foils. So nowadays in CBM experiment we will use triple gem. In ALICE experiment, in ALICE TPC end cap, we will use quadruple gem, 4 gem foils. And you can also see from this curve or this gain plot that when you are using single gem, to achieve a gain of the order of 10 to the power 3, that means if the primary electrons is 10 here, then here the number of electrons is 10 to the power 3 into 10. So that is called the gain. Gain means output charge divided by the input charge. Output total number of electrons here at the output divided by total number of electrons in the primary ionization. So this is called gain. Now you can see 10 to the power gain is achieved in 10 to the power 3 gain is achieved using single gem, where you have applied voltage in the single delta V in one gem foil up to 500 volt or even more. Whereas if you have used double gem, you have achieved almost 5 10 to the power 3 at 440 volt only. Whereas you have achieved even more gain at lower voltage when you are using triple gem. So you can see you are getting more and more gain at low voltage using cascade of gem foils. So now I will show how we build small prototype gem detectors. So this is one gem foil. So this is Kapton part, and this part is the gem part, and you can see 2 copper leads are also created. So this is top and this is bottom. So you can see this is visible, this copper part is visible, and this is not clearly visible because this is on the other side of the Kapton, and this Kapton is 50 micron thick. So first we need to do the stretching of this foil. How we do it? We do basically using a frame. So there are many ways of stretching. So what I am showing here, this is only for making small prototypes for lab testing, but for large detector there are other techniques, like in CBM experiment or CMS experiment of CERN, they are using no glue, no not thermal stretching they are using, but here we have used glue, and this is called thermal stretching. How we do it? First, this gem foil is kept inside these two frames. These frames are made by plexiglass material. This is also some kind of plastic. This is available in India as well. And there are screws. Using these screws, mechanically we tighten the gem, and then we just apply heat to increase the temperature, and because of increase of temperature and different expansion coefficient of Kapton and this glass epoxy material, there will be a stretching kind of thing. And once it is stretched, what we can see visually even, and then we put with glue this frame from top and from bottom, and we give some time to cool down the whole thing. Now when this whole thing cools down, then again this compression or expansion coefficients are different for the different materials. So but since in these frames we put glue, so glue these glued frame are placed on the gem, and these gem frames are stretched, and then we cut this part from this side, okay, keeping these two parts, because these two leads we need for application of high voltage. So this is done. We have done it at CERN, we have done it at GSI, and also we have done in VECC, NICER, IOP, Bose Institute. In many places we are doing these things on regular basis. We are building these detectors. Now these are other components to make the chambers. So this is the readout plane. So this will be kept at the bottom. These are the Kapton window. We will show how we put these things. This is plastic frame to make the gas chamber. These are O-rings. This is very important component. You will, whoever who will work with gas detectors, for sealing of any detector where you need a provision that I need to open the chamber again. So two hard surfaces cannot be joined properly if we don't use this is called gasket in between the surfaces. Otherwise there will be a leak. So when you are joining any two hard surfaces, between these hard surfaces you need a component called gasket. So we usually used O-ring gasket, but other gaskets are also used to build the detectors. So there are some spacers to keep the constant or fixed separation between the gem foils. As I told, we usually build triple gem, quadruple gem, so we need uniform separation between the gem foils, and also we need gas nozzles for gas inlet and outlet. So these are the general components. So these components and the picture what I am showing, this is only for small prototypes. So these detectors you can build in your institute whenever wherever you want to set up a lab. So this is the first step you need to do. Now how we build small gem detector prototype. So I have some time, so I will go. So this is gem foil again. So we do stretching. Now you can see this is a stretched, all this foil is already stretched. Now you can see this is one surface without stretching, and this is after stretching. You can see. So this is done. Now after that, I will cut this in proper size. Now first I take the readout plane. On the readout plane, I will put 4 spacers, and then I will put 1 gem foil. So now you can see it is cut. I think I put here all 3 gem foils. So this is 1. This is so 1 gem foil. I need 2 leads. So you can see 1, 2. You can see 3, 4. You can see 5, 6. So 6 layers are there. That means 3 gem foils I have already put. Now on top of it, I have placed the drift plane. Drift plane is nothing but another plane, but there is no hole. Only one side there is Kapton and another side there is copper. Same like it is same like gem foil, but there is no hole. I don't need it because it is not used for amplification. This is only to give nominal voltage and to make the drift gap so that there is little voltage and you can drift the primary electrons towards the gem plane. So now you can see I have placed the gem this frame, and you should keep in mind that on the bottom also, because this is hard surface and I am placing this frame which is another hard surface. So I have used 1 O-ring at the bottom as well. Okay, so I have placed the O-ring, and on the top also I have placed this O-ring, this one, and this is at the bottom because the 4 screws are here inserted, but this chamber itself will be gas tight. So I need to use araldite to seal these holes, because the support, the pillars, that means these plastic screws are there. Now from top of it, I have placed the cover plate, and this is the this is also capped on to make the to assemble the gem. And now these are the nozzles for application of gas. So this is complete assembled gem detector, and with the high voltage divider network. I will show in detail also, and you can see these 4, 1, 2, 3, 4. These are some electronics board where you can see the connectors here. Here actually in the readout there are large number of pads or strips for collection of signal, but for the prototype chambers where we do the routine study or some basic R&D, there we sum all the connectors and we take 1 signal from each connector. So we usually get 4 signals, and these signals are collected using a cable, and you will hear in your lab as well. This is called LEMO cable. So this connector is provided from CERN, which is basically built to sum all the readout strips, and we will get the signal and take the signal using LEMO cable. So this is our lab at Bose Institute, where our students are working and studying many aspects of the detectors. And this is one triple gem detector. I will also show some videos where you can see in real time how these detectors are used. So this is one detector. The high voltage is applied, and these high voltages are distributed among individual 3 gem foils. And because we are using triple gem, so I need 3 delta V's: delta V1 for first gem, delta V2 for the second gem, and delta V3 for the third gem. So accordingly we need to distribute the voltages for that. And this is the gem detector where we place the source. We usually use iron 55 X-ray source where we get nice spectrum, and we can see the signals in the oscilloscope. And this is the schematic how we take the signal, and finally we see the spectrum and count the signal. So typically we use argon CO2 gas in 70-30 ratio. We also change the ratio, sometimes 60-40, 80-20, 90-10, different ratio we are using. We used fixed gas flow rate, that also we change if required. For the R&D purpose, we use conventional NIM electronics. NIM stands for Nuclear Instrumentation Module. You will find the details in NOL or LEO instrumentation books that you have to read in your course. I am sure that you know about these books. And we have basically used a special preamplifier for our detector, that we got from Heidelberg. And finally, these signals from preamplifier we put to a linear FIFO. It is very interesting module where we basically get 4 identical analog signals. So here we get analog signal, it goes to linear FIFO input, and from there I can see 4 output of same type and same pulse height, same frequency, and then one signal we put to SCA, which we use as discriminator, and then we put that signal to NIM TTL adapter, and then finally we count this signal using NIM scalar. Another signal, analog signal, we put to MCA. MCA stands for multi-channel analyzer. This SCA stands for single channel analyzer, and then we see the spectrum in the computer. So this is general electronic setup, and we basically use this simple setup for most of our study with gem detectors, with straw tube detectors. I will show the pictures. And this is the schematic, electronic schematic for voltage divider. You can see we usually give negative high voltage here, and there is one filter to block the AC component because we apply DC here, and this is drift plane. And before this plane, we usually use one high resistor. This is used as protection resistance. So I will ask you to answer, if you can, that why this protection resistance is used. Just simply, this is very you can use just network theorem, that protection means if there is any spark, so this high resistor, this 10 mega ohm resistor, will limit the spark and it will save your detector. How? So that I am just asking. Many of you cannot answer, but some of you definitely can answer this question. You just try and you email the answer to me. Okay. Now I apply high voltage here after this filter, and then there is voltage divider. So current is going from here to here, so there will be a potential difference, and it is grounded. So that means this part is more negative than this part, and so on. So electrons will move this direction, and there will be multiple avalanches. So finally, we collect the signal from the readout plane. So this is again this oscilloscope signal, how we see the iron 55 signal in the oscilloscope. And now I will give, let's say, 1-2 minutes. So how we calculate the gain? Basically, we get a spectrum where there is you can see in the x-axis it is called ADC channel number. ADC channel number, or you can also say it is the energy. If it is calibrated properly, so this peak will correspond 5.9 keV energy, because iron 55 main peak is 5.9 keV. This is another peak. This is called escape peak. It is something like at around 3 keV, and here it is count. So it is kind of you can say it is a histogram. So x-axis is energy, y-axis is count, and we usually fit this main peak. That means I calculate that with this 5.9 keV energy deposition, how many electrons are produced. This number is called primary electrons, and it is calculated here with 5.9 keV gamma ray. When it is fully absorbed in 70% argon and the 30% CO2 gas mixture, it produces 212 electrons. So this number is called primary electrons. So these primary electrons are created in 70-30 gas mixture after the absorption of full absorption of 5.9 keV X-ray. And when this is collected, finally I see the the spectrum, and in the output I get the output charge from the spectrum, and using this formula, and this is mean. So this mean means this mean, and then I use the preamplifier gain. That means preamplifier collects some charge in femtocoulomb and gives you output in terms of some millivolt pulsate signal. So from this calibration curve, I get the total number of output charge and primary charge after absorption of one full absorption of one gamma this X-ray from iron 55. I get the input charge, and finally I calculate the gain of the detector. And also we measure another thing called energy resolution. So if you feed this curve, you will get one mean, another called sigma. So from this we calculate the energy resolution of the detector. So this is very simple calculation, but we need to do the measurement in a very hard way, because sometimes we don't get any signal after doing everything. So whoever is working with detectors know to see a signal and to count it and to get the signal, to see the spectrum, how interesting, how encouraging those things once you do it. So this is one just typical gain and energy resolution plot. Shayok, I think one of our students have made this. So now I'll show some videos if I have some time. Obi, I can show 1-2 videos, right? And if Shubikash is waiting, then maybe Shubikash, are you there?
Yes,
Can you
sir.
hear me?
Yes,
Shubikash.
Shubikash.
Yes, can you hear me?
Okay, yeah, I can hear you. Okay, so I'll
Yeah,
show.
I am there, but you can take your time, no problem.
Okay, no, I'll show just 4 pictures and then 4 videos small, and then I'll
Yes, please take your
finish.
time, no hurry.
Yeah, I'll finish. No, then you have your lecture also. So anyway, so let me. So yeah, so you can see some electronic modules are there. So this is high voltage module. You can see there is a model number. We use model N1470, where I can using these knobs, I can do many things. I can apply voltage. You can see Vmon, this means voltage which is monitored, which is 500 volts. Some currents are there, and there are some other models. 3-fold logic unit. You can see these modules I have talked about in the circuit diagram. This is quad linear fan-in fan-out model, and then this is SCA. TSCA means timing SCA, single channel analyzer. And there are some other modules, TAC, time to amplitude converter, which are used NIM to TTL converter, NIM TTL adapter, you can see, and quad scalar. Scalar means counter basically, and 16 channel LED. LED stands for leading edge discriminator. This is another high voltage power supply what we use in our lab, and then function generator or pulse generator for standard pulse production. Then again scalar, some dual timer modules, 3-4 logic units, and many cables you can see which are used completely non-professional way by me and by my students, but for the sake of physics we had to do it, and we got some results at least. So this is another video. You can see this is the gem foil. Shayok has used for his charging up study. And you can see how high voltage connections are made here, you can see. And these are the voltage divider network. We have built it in our lab, but this detector we got from CERN. And this connector is called SHV connector. So who will use or will work on detector, you have to use these connectors and these detectors in a frequent way. And this is this connectors called Panasonic connector for the signals connected with the PCB. Okay, you can see closely. So these marking are also done in a non-professional way, but yeah, so he has also done the uniformity of performance study. This is the sum up board I was talking about, and you can see with the sum up board one small LEMO cable is connected, and this LEMO cable will go to the preamplifier for the collection of signals. So yeah, so this is the LEMO cable, this is coaxial cable. You have to read about the coaxial cable and signal processing as well. So we will not cover in this lecture. So this is another gem detector. That was this last one was double mass gem detector, triple gem. This is single mass gem detector. All 10 by 10 small. So this is the only gem part. So this is the cover plate. You can see this cover window, and the drift and all 3 gem foils are inside. So this is high voltage connector. The divider are there here. We have used this copper plate for the shielding purpose, electromagnetic shielding. So this is preamplifier. So this preamplifier is input is here, and it is going to the electronics. After preamplifier, it is going to linear FIFO in. You can see from this in 4 signals we have taken. One we have here you can see one is fed to SCA, where Shayok used this SCA as discriminator, and one we have put to MCA for the spectrum. And this is last video for today. So you can see this is closed gem. Iron source is used. So 5160 volt we have monitored. Current is 729 microampere. You can see how the signals are coming using the source. And if you see this is in the oscilloscope, and if you go to the MCA and in the computer, you can see how the spectrum is generated. So you see what I have shown. This is the main peak. It is accumulating the data, and this is the escape peak. So the resolution is not very good because these 2 peaks are not separated nicely. So this is the MCA. The signal from this FIFO to this MCA are fed using this cable, and this MCA also needs a power what we put from backside of this MCA. So this is this spectrum in the MCA output. So it is visible, you can see. So here also you can measure what is the peak or what is the channel number where we obtain the main peak. So all the analysis also you can do it here in using the software provided by the MCA, or you can store the data and you can use your root analysis package for analyzing the data later on. Okay. So yeah. So these all are done in our Bose Institute lab. Okay. So so tomorrow maybe I will show the fabrication of large gem detectors, and I will try to show some other detectors what we have fabricated in our lab or by our students or by our collaborator. Okay, so I am stopping here today. If you have any question, you can ask me or you can write to me anytime. Yeah, that's all for today.
Excuse me, sir. Can I ask question?
Yeah, sure.
Yeah. So I just have some basic questions, I would say.
Yeah,
If we, you mentioned that, so if we increase the gem foils, we get the better gain for lower voltages, right?
Yeah, individual lower voltage,
Yeah.
lower voltage, yes.
So and you mentioned that Alice used quadrupole
Gem, yes.
gem and CBM using 3 layers.
Right.
Is there any limit? I mean, can we add any number of foils?
Yes, the very good question. Yes, there is a limit, because if you see one of my slide, I don't know. If you go in this, I have shown somewhere this. Yeah, here you see, if you start increasing, if you see, let's say you have put your readout pad somewhere here, so you can see in spatial direction also this is spread, right? Okay, so now if you increase this number to a large value, say 10 gem foils, now after this avalanche, it will be spread. So then there will be a problem of position localization. So you will get a big some cluster kind of thing, and many pads will be fired, and then for one single particle you will get signal from many pads. So that we don't want, first of all. Another thing is, to generate this thing, there will be some timing information involved, right?
Yes.
Okay. However, this gem detector has not very good time resolution. It is of the order of say tens of nanosecond, whereas in RPC you will get time resolution better than 1 nanosecond, or even if you use multi-gap RPC in like your ALICE. So the timing information will also be affected if you increase this number to a large value. Okay, so two things I told: physically time resolution and position resolution will be bad. Another thing is the cost. This is physics point of view. Another thing is your cost will be very high. If you can achieve your required gem with 3 gem foils, with all your physics purpose, physics goal solved, then you don't need to increase this number. Like whereas in ALICE we are using 4 gem foil, we are in CBM we are not using, because the purpose is different. Okay, so you have to optimize this number. Accordingly, you can select how many gem foils you need.
Okay. So this distance between 2 gem foils,
Yes,
that is 2 mm. Obviously, it must have some optimum value.
Right, exactly. Again, nice question. Yes, there is some optimization. Lot of R&D was there. Lot of simulation was there. Both all in ALICE experiment, for CBM experiment, for CMS experiment. All experiments have done. Lot of simulation. You will find lot of papers, and also experiment or R&D was there to finalize these gaps. So this gap, what I talked about, 3 millimeter drip gap, 2 millimeter, 2 millimeter, 2 millimeter. These gaps are called transfer gaps, and this collection gap. These are you can say this is mostly CMS people are using, and CBM will also use this gap. But in CBM we have done R&D with other gaps also. Like this gap is 1.5 millimeter. This is 0.5 millimeter, 0.5 millimeter. All kind of R&D people have done. Okay, so there is optimization as well. You are right.
Okay. Okay, no problem. Thank you, sir. Thank you.
Okay, thank you. Any other questions?
Hello, sir.
Yeah, please.
Sir, while calculating the total number of primary charge particle produced,
Yes.
you have taken the concentration of argon atom as well as the concentration of carbon dioxide.
Right.
Sir, but carbon dioxide gas is not responsible for ionization of electrons.
No,
it is only
thing is that you see, carbon dioxide gas is used for quenching. That you are right, you know it. But if there is, let's say there is a gas mix, let's say there is only one gas. Okay, there is only
Yes.
one. You can see my slides, or is it okay?
Yes, sir.
Okay, so let's say there is only one gas, gas X. Now one particle or one X-ray incident with some energy, E gamma. Now this E gamma is fully absorbed by it. Now you know, to ionize this gas, let's say ionization potential. So to this much energy is required to ionize a gas molecule. Okay, to produce one electron or electron ion pair. Now you know how much energy is required for one electron ion pair, that is, let's say X. Now if you have E gamma of energy, now E gamma divided by amount of energy required for one electron ion pair production, it will be the total number of electrons, right?
Yes, yes.
If there is only one gas. Now if there is any gas mixture, now although the reason is different, but that charge particle does not know why you have used CO2 for quenching. It will come, it will interact, what it will see in his path, right?
Sir, is there any possibility that carbon dioxide gas is responsible for? Is there any probability that carbon dioxide is also responsible for ionization?
It is responsible. That's why we are using 212. I don't know. I mean, I cannot tell that there is no ionization in the carbon dioxide. I cannot tell that there is ionization only in argon. Carbon dioxide is only for quenching. That's why I cannot tell, because I am using a gas mixture and charge particle is coming. It is interacting with both.
Yes, sir. Yes.
That's why I use this formula as a thumb rule kind of thing. If you have more number of gases, let's say 3-4 gas mixture, in case of RPC we do it, then you have to use another formula. I mean, this factor will be more and more. Okay.
Yes, sir. Thank you.
So you cannot tell that our CO2 is not ionizing in the gas mixture. There is some, definitely. Okay. So maybe I have to stop, because I have if you have any question, you can write to me anytime. If you know my phone number, you can write to me, or you can WhatsApp me. If you have any question, you can anytime, you can call me also. Okay. Okay, so